Okay, so today we have the thesis defense of Sameh Rafee, who is a graduate student at IAG, the Institute of Astronomy, Geophysics, and Atmospheric Sciences, and this is a joint program with the Lund University in Sweden. And I think, if I'm not right, it's the first one in the Department of Atmospheric Sciences. There's a joint defense. And we have, as members of the committee, the Ph.D. committee, well, Edmilson Freitas is the advisor. Cynthia is the advisor from the Lund's point of view. A co-advisor is Jorge Martins. And as members of the committee, myself, Pedro Dias from the IAG, Daniel Dalazia, I think he's from Santa Maria, Federal University of Santa Maria, right, Daniel?
Yes, Santa Maria in southern Brazil.
Santa Maria, exactly. And let's see, Neda Hidalgo from Unicamp, and Humberto Rocha, who is also from the Department of Atmospheric Science at the USP. So you have about 50 minutes to present your work, and then we'll proceed to the questions by the committee members. Okay, you can go on.
Pedro.
Oh, Cynthia, I forgot about Cynthia. Right?
E Andrea.
Cynthia is a advisor also. Sorry.
Andrea Cardoso.
Andrea Cardoso. Yes, that's right. I forgot. Andrea Cardoso is also a member of the committee. She's from. I always forget the complete name of your university. It's Andrea. Help me. It's what's the
Federal
official?
University from ABC.
Yeah, UF Federal University of ABC in here in the state of São Paulo, and so I'm okay. So now it's complete.
Okay.
Pedro.
Yes.
Please ask everybody to turn off the microphones.
Yes. Please turn off the microphones because otherwise we have an echo problem, and it's going to be difficult to hear. I think everybody is off. No.
Okay, and start. Good afternoon and good evening, everyone. Thanks a lot, Professor Pedro. I also would like to thank the members of the board. I'm glad that all of you accepted the invitation, and I'm grateful for everyone who is watching at home. I know that there are people from Brazil, from Sweden, and even from Lebanon. بتشكر أهلي وقرايبي من لبنان ومن البرازيل وكل الجيل العربي. أنا كتير مبسوط الموجودين معي أونلاين. إن شاء الله عقبال ولادكم. شكرا كتير. Okay, I'm back. I would like to say that even you are not here, I'm very happy and excited because I know that you are fine and I know that you are safe at home. And I want you to know that I can feel the energy of each one of you with me today, and I will use it to do this presentation. I would like to start by a question that has puzzled me for quite a while. How much land use and cover change or precipitation change can affect the hydrological process at a large-scale basin? I'm going to cover these two issues today at the Upper Paraná River Basin. But why did I choose this basin? What's so special about it? To answer these questions, I would like to invite all of you that are at home to come with me, the second largest and one of the most important river basins in South America, the La Plata River Basin. The main river of this basin is the Paraná River, which is the river that aroused my curiosity. And this research focused on its upper part, that's called the Upper Paraná River Basin, which covers 6 Brazilian states and a small part of Paraguay. This basin has a drainage area more than 900,000 square kilometers. The Paraná River has its sources at the confluence between Paranaíba and Grande rivers, together with other important rivers, are responsible for the Paraná River has a mean discharge of about 14,000 cubic meters per second. This basin has a significant role in the Brazilian economy, being a home of more than 65 million inhabitants, and also has a great importance in energy generation, which houses more than 150 hydropower plants, having the largest installed capacity in the world at the Itaipu Dam. What's happening to this basin is that it has undergone an expressive changes in its hydrology. For instance, if we look at the historical annual discharge at the stream gauge close to the river mouth of the basin, we can see through this graph that the annual discharge since the 1930s until the 1970s has a median of about 8,500 cubic meters per second. However, after the 1970s, a shift in annual discharge at the lower Paraná was observed. If you compare these two periods, it represents an increase of about 26%. Studies associate this and other hydrological changes over the basin to land use and cover change, mainly happened during the 20th century. For instance, here we have the spatial distribution of Cerrado, which in 1985 covered 22% of the basin area. It would surprise you if I say that after 3 decades, until 2015, Cerrado had a reduction of more than 170,000 square kilometers. On the other hand, a global event known as climate shift was witnessed, mainly during the 1970s, which defined as a short period where the climatic oscillations changed their phases at the same time, leading the climate to a new state. According to several researchers, this event changes the precipitation pattern over the basin, which could possibly affect the hydrology. So considering the importance and the uncertainties about the basin, this research aimed to fill this gap by answering how are the trends of seasonal, annual, and extreme precipitation events in the Upper Paraná River Basin. What are the hydrologic responses to land use and cover change happened in the latest decades, and to which extent are changes associated with observed land use and cover and climate shift responsible for the increase in the discharge of the Paraná River? The first part that was done in this project was the collection of precipitation data. Daily precipitation was collected since the beginning of the 20th century. As we can see here in this spatial evolution of the installation of the rain gauges over the basin. For trend analysis, it was selected the stations that have a time series between 1977 and 2015-16 with less than 10% of missing data and presenting homogeneity. Following these criteria, a total of 853 rain gauges were selected. The trends were investigated by the main candle test, and the statistical evidence against the null hypothesis was evaluated through the bootstrap method. The main candle was applied for 9 precipitation indices, as we are going to see in the following slides, and the climatological mean at each of these indexes was interpolated using the inverse distance weighted method. So here we have the results, and we have the spatial distribution of trends and the interpolated values of annual and seasonal precipitation totals. In the blue pattern, we have the interpolated values. In the black triangles, we have the positive trends, and the red ones are the negative trends, both at 95 confidence level. And the black circles are the not significant trend over the basin. So we can see here that the most of the negative trends are located in the northern part of the basin at all season and also at the annual precipitation totals. On the other hand, the positive trends are located mainly in the southern part of the basin, mainly in summer season. Regarding the extreme precipitation events, here we have the trends of the annual greatest 5-day total precipitation and the trends of the number of days with precipitation higher than 50 millimeters per day. At both cases, we can see that most of the positive trends are located in the southern part of the basin, which is a matter of concern because, for example, many of these trends are located over areas with a climatological mean of 9 days per year with precipitation higher than 50 millimeters per day. Regarding the trends of the maximum of consecutive dry days, we can see here that most of the trends are located in the northern part of the basin, also a worrying case as they are over areas with 90 consecutive days without rainfall. And finally, the mean precipitation per rainy day, we can see clearly that most of the trends are positive, indicating a lengthening of the wet season at most of the areas of the basin. The next important aspect that I would like to discuss today is the hydrological responses to land use and cover change, which was estimated by the hydrological model, soil and water assessment tool, the SWOT model, with the modified plant growth model. With this model, it was simulated 37 years between 1979 and 2015, where the first 5 years using for warming up the model, the following 22 years for calibration, and the last 11 years for validation. First and foremost, it was prepared all the input data for the model that includes climatic and physical data. The climatic covered the daily precipitation, which in this case it was used almost 2,500 rain gauges with different data availability, and then these data were further interpolated using the inverse distance weighted method. Regarding the other variables, it was used the daily outputs from the climatic forecast system analysis. Regarding the physical data, the topography data was based on the digital elevation model at 90-meter resolution. For the characteristic of soil, it was defined 15 classes of soil. And finally, for the land use and cover, as a reference, we used the classification from 2015 and defined 6 major classes: forest, cropland, grassland, water, urban, and cerrado. Using this data, the hydrological model for the basin was built with the highest possible discretization allowed by the model, where the basin was divided into more 5,187 subbasins, and these subbasins were further divided into more 44,600 hydrologic response units, using a combination of the defined threshold of 5% for land use and cover, 10% for soil, and 20% for slopes. At each of these subbasins, it was calibrated the monthly discharge and the monthly leaf area index values. For monthly discharge, it used the automatic calibration using the sequential uncertainty fitting algorithm. In this case, it considered 20 parameters, mainly regarding to soil and groundwater. And the strategy used for calibration was the relative change, where the current value was multiplied by a factor ranging positively or negatively between 40 and 80%. For manual calibration, it was considered the parameter related to plant growth to adjust the leaf area index during the period. For the performance of the calibration and validation, it was selected 5 statistical indices: Pearson bias, coefficient of determination, net Sutcliffe, Lin-Gupta, and the root mean square error. The calibration, the discharge calibration, covered 78 river outlets. First, it was selected the upstream subbasin that presented satisfactory performance according to the statistical indices presented previously, and then to optimize the calibration, the hydrological project for the whole basin was divided in 9 SWOT projects and applied the simultaneous multi-site calibration. What does this method do? Let's suppose that it wanted to calibrate the outlets over the Tietê subbasins. So first, it was calibrated the first order outlets, which are independent, then the second order outlets, then the third order outlets, and so on. Always starting from upstream to downstream outlets and also from the created project. And the values of the fitted parameters were used in the initial project for the whole basin. So here we have the results of the average monthly simulated forest leaf area index at 34 major subbasins. We can see here that it was achieved a satisfactory seasonal variability, where the highest values are up to 5.5 during the wet season from October to March, and the lowest values from 2.5 during the dry season from April to September. Cerrado had similar seasonal variability, but with values ranging between 0.5 and 2.5. And finally, grassland from 0.5 until 2. Moving to the discharge simulations, here we have examples of the monthly discharge against the observed data at the largest rivers of the basin, at Paranaíba, Grande, Tietê, Paranapanema, Iguaçu, and also close to the river mouth of the basin at the Paraná River. We can see that it was achieved a satisfactory simulation. For example, if you consider the periods of calibration and validation, the statistical indices of coefficient of determination and net Sutcliffe achieved values higher than 0.7. With this model calibrated and validated, it was simulated 2 different land use and cover, one from 1985 and another one from 2015, with unchanged climatic conditions between 1979 and 2015, and the first 5 years used for warming up the model. The effects of land use and cover change, it was addressed at 34 major subbasins. And I selected some of these subbasins that I will discuss with you in the next slides. But before that, let's take a look for the whole basin at the spatial distribution of long-term means of surface runoff, evapotranspiration, and soil moisture, given the difference between the scenario from 2015 minus the scenario with the land use and cover from 1985. It was calibrated for annual, for wet season values, which in this case considered from October to March, and dry season from April to September. We can see here that the land use and cover change increased the surface runoff and the soil moisture and decreased the evapotranspiration at most of the areas during the wet season. These changes, one of the main causes is the agriculture expansion. As we can see in this spatial distribution of cropland, where in red are the loss areas, in blue are the gain areas, which are most of them over the basin, and in green are the no change areas between 1985 and 2015 over the basin. For example, if we look at the upper and lower Tietê, the total gain are higher than 15,000 square kilometers, which likely changed the hydrology over the subbasins. If we look at the lower discharge, the river mouth of Tietê, we can see here through this graph that represents the percentage of discharge changed, that the land use and cover change led to increasing discharge during the wet season up to 10%. On the other hand, led to decreasing discharge during the dry season up to 5%. These changes could be explained by the hydrological processes, as we can see here in these two box plots that represent the interannual variation, considering the mean values of the upper and the lower Tietê. So we can see here that the surface runoff, which is one of the main contributors to discharge, increase their values together with the soil moisture during the wet season. On the other hand, decrease their values during the dry season. And we can see here that the land use and cover change led to a reduction of evapotranspiration during the wet season. This pattern was observed at many other areas of the basin. If we consider all the hydrological responses and look at the river mouth of the basin, we can see here that the land use and cover change led to increase the discharge of average of 4% during the wet season and decrease discharge during the dry season of average of 2%. Let's move one step forward and see the integration of land use and cover change and climate shift together. It was used the same hydrological model, but the simulation were performed during 1956 and 1990 with the first 5 years using for warming up the model. It was simulated 3 simulations with similar climatic, which in this case used 2,300 rain gauge stations and with the same soil and topography. But these simulations were performed with 3 different land use and cover. One from a pristine period, another one from 1960, and another one from 1985. How it was constructed, these 3 land use and cover. So first, the land use from 1985, it was the same as described previously with 6 major classes. For the map from the unchanged landscape, the different categories of forest was grouped as a unit class as forest, and the different savanna physiognomies was grouped as cerrado. And finally, for the land use from 1960, it was created based on the mapping products that provide the estimation per pixels of cropland and grassland. Some criteria was adopted to reconstruct this map, where pixels lower than 15% were defined as natural vegetation, forest, or cerrado, according to 1985 and to a pristine period. On the other hand, pixels higher than 15% were defined as cropland or grassland according to the highest percentage. And finally, the urban and water areas followed the map from 1985. So here are the results of the tree-generated map. Overall, we can see that the east part of the basin had the greatest natural vegetation suppression, where forests decreased from 57% to 36% in 1960 and to 18% in 1985. And Cerrado had a major reduction from 1960 and 1985, where almost half of the original area was suppressed. But how it was addressed these changes together with the precipitation change related to the climate shift. For that, it was constructed discharge scenarios in order to compare the land use and cover change between 1960 and 1985 versus climate shift. In this case, it was considered that the climate shift, following previous studies, that happened in the mid-1970s, between 1974 and 1977. So the effects were evaluated between the comparison between 13 years before the climate shift and 13 years after the climate shift. And it was addressed only land use and cover change, only climate shift, and both effect. For that, 5 scenarios were created. In scenario A and scenario B, it used the same discharge period, but with different simulation with land use and cover. For instance, here in scenario A, we have the discharge period between 1961 and 1973 with the simulation from 1985, minus the same discharge period, but with the simulation from 1960. On the other hand, the climate shift, it considered 2 different discharge periods, but with the same simulation. For instance, here we have in scenario C the discharge after the climate shift with the simulation from 1960 minus the discharge before the climate shift with the same simulation, in this case from 1960. And finally, scenario E, it considered 2 different discharge periods and 2 different simulations with land use and cover. Now, the comparison between land use and cover change from a pristine period until 1985 versus climate shift, the same criteria was adopted. But instead using the land use and cover from 1960, here we use the land use from a pristine period. Before we look at all the results of all these scenarios, let me show you what's happened with the precipitation after the climate shift. So here we have the interpolated values of the precipitation relative change, considering the average annual median precipitation under the period after the climate shift relative to the period before the climate shift. So we can see here that the precipitation increased after the climate shift at most of the areas, mainly in the southern part of the basin where the increases are higher than 20%. Only a specific areas of the basin, mainly in the northern eastern part, were presented a reduction in precipitation. So now that we know a little bit about what were the land use and cover change and how much was the precipitation change, let's see how these changes affected the discharge values. For that, it was selected 10 outlets at the largest rivers of the basin and calculated the relative change in the average annual median discharge within the scenarios. So we have here the land use and cover change between 1960 until 1985 versus climate shift. We can see here that all the scenarios indicate increasing discharge, and the climate shift scenarios, which are illustrated in blue colors, indicated higher increases compared to the land use and cover change scenarios. This happened at all the largest rivers of the basin. For instance, if we look at the lower Paraná, the river mouth of the basin, we can see that the increases are up to 6% related to land use and cover, more than 30% to climate shift, and if we consider both effects, this reached 38%. Now, the land use and cover change from a pristine period until 1985 versus climate shift, again, we can see that all the largest rivers, the climate shift is the main driver in the increase in discharge, except for lower Tietê, which the main driver is the land use and cover. And again, if we look at the lower Paraná, we can see here that if we consider both effects, the increases are higher than 50%. With that, we have come to the end of this presentation, and I would like to end saying that the upper Paraná river basin has experienced changes in precipitation. In the last 4 decades, in the northern part of the basin, presented a decrease in seasonal and annual precipitation totals, which possibly increased the number of consecutive dry days. In contrast, in the southern part of the basin, an increase in the extreme precipitation events was observed related to rainstorms, which possibly increased the summer and annual precipitation totals. And most of the areas of the basin presented an increasingly long rainy season. In addition, in the last decades, between 1985 and 2015, the natural vegetation suppression, replaced mainly by grassland and cropland, caused an increase in the surface runoff and soil moisture during the wet season and decreased their values during the dry season. Also, the basin had an expressive reduction in evapotranspiration during the wet season. These changes caused an increase in discharge during the wet season and decrease in discharge during the dry season. And if someone asks me, who is the main driver in the discharge at the lower Paraná River? Past land use and cover change or climate shift? I would say both. Both had an expressive impact on the discharge at the largest rivers of the basin. However, the climate shift being the main driver. This is because in 1970s, the climate shift caused an expressive increase in precipitation, mainly happened in the southern part, close to the river mouth of the basin. I live here saying to the basin that I grow up almost my whole life, that besides the possible future land use and cover change, global climate shift may occur again in the next decades. Whether positive or negative it is, together with the land use and cover change, it will affect several sectors of economy, such as water supply, energy generation, or even increase the risk of floods at many areas of the basin. Along with this statement, I would like to leave you by a personal reflection, saying that everything in life has the same importance until the moment you give value to each of it. Thank you very much.
Thank you.